did all of them except for the a as a function of x case. So we'll deal with that case today. I think that the problem I want to do with that case alone is going to take about 20 minutes. So by the time I deal with that problem and leave a little bit of time for the computer program, I didn't want to start a new topic. The new topic we'll be doing next is looking at energy and momentum methods when trying to analyze one-dimensional motion. Chapter 9 that we're working with is one-dimensional motion. After we master one-dimensional motion, we move on to two-dimensional motion, three-dimensional motion, etc. So I'm not going to get into the energy methods and momentum methods today. We'll worry about that on Monday. What I'd like to do today to start, though, is give another example of graphing. I graded your quizzes. Not all of you got those multiple choice questions right. The last two questions on the quiz that we took on Wednesday were basically being able to read graphs and discern information about position, velocity, acceleration. So as such, I'd like to do another example with that, try to help those of you who are having a little bit of trouble there. The example I'd like to do today is a example where I take a marker and I throw it up like that. Okay? So very easy to act out. There it was. Okay? And I'd like to see what the graph should look like for position, velocity, and acceleration. Let's start by trying to make a graph yourself let's start in the middle. So instead of graphing the position versus time, let's try to graph the velocity versus time. So the actual situation is going to look like this. Start, 0. So I want your graph to start, then I throw it up and catch it, and then maybe a second after that, stop your graph. Okay? So go ahead and think about it and see if you can make a guess of the velocity versus time graph that would result from that situation. Go ahead, Andrew, if you want to make a guess yourself. Are you taking physics now also? So see if you can make a graph of the velocity of the marker as a function of time. We'll consider up to be the positive direction. Okay. About maybe a third right, 2/3 wrong for the most part. Let's try to think through it a little more slowly now, and maybe work in some information that you might know from physics. After I let go, assuming there's very little air drag, which would be true for this short throw, after I let go, what's the acceleration of the marker?
It's at its greatest.
Well, two answers. Negative 9.8, Ryan's saying. And James, you had a comment on when it's greatest? Or?
Well, you said it's velocity as soon as it leaves
No,
your hand?
it's acceleration.
Oh.
As soon as I let go,
Negative 9.8.
negative 9.8. Which way is it accelerating? So as soon as I let go, which way is it moving?
Up.
Up. Yet it's accelerating down. Halfway up, what's the acceleration?
9.8 meters per second.
It's still negative 9.8 meters per second. Because there's a force acting on it downwards. So the only force acting on it that's important here is the force of gravity. Technically there is an air drag force, but we're ignoring that. So the only force acting on it is mg down. So if you did F equals ma, you'd have negative mg, which is the only force, equals ma, so the m's cancel, and you get the acceleration. How about 3/4 of the way up? Roger, what's the acceleration? How about the top? What's the acceleration?
Negative 9.8.
Negative 9.8. There's a possible source of confusion. Some people think at the top there's something special going on with the acceleration. At the top, the only force acting on it is force of gravity, so therefore the acceleration is negative 9.8. What is the velocity of the marker at the top?
0.
0. So I have 0 velocity, but not 0 acceleration. That's no problem. But again, some people come into this course, or come into a physics course, bless you, with a misconception that if I have zero velocity, I've got to have zero acceleration. That's not true. In fact, for example, at the top, I have what acceleration, Roger? Negative 9.8, and the velocity at the top would be 0. Okay, so I'm expecting a constant acceleration. What does that tell me about the slope of my velocity versus time graph between when I let go and when I catch it? So the slope of my velocity versus time graph, what is that exactly? It should be linear, it should be a straight line, and the slope should be a positive or negative slope. Negative. When I first let go, is the velocity positive or negative? Positive. So let me draw the graph. Let me skip before I let go. And I will start with some time where I let go. When I let go, my velocity is positive, so some positive number right there. This is where I'm letting go. After I let go, and I'll put my 0 here, the instant after I let go, does the marker speed up or slow down?
Slows down.
Slows down. So, and Zach told me that it should be linear, meaning it should be a straight line, because the acceleration is always negative 9.8. The acceleration is the slope of the velocity versus time graph. So, the slope should be a constant. My velocity starts off as a positive number, gets less and less and less and less and less, hits 0, then goes negative. Where on this graph is the marker at the top?
Up to 0.
Okay, so right here, the marker is at the top. How we know it's at the top is because at the top, the velocity is 0. So at the top, the velocity is 0. Okay. When I catch it, if there's been no air drag, when I catch the marker, if there's been no air drag, I'm not proving it to you right now, but if there's no air drag, the instant I catch the marker is going to be moving at the same speed downwards as I released it going upwards. So if I let go on the way up of 5 meters per second, it's going to go up, 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 stop, come down, 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 and be moving at 5 meters per second downwards if I catch it at the same spot. So that point, the distance of that away from 0 and that away from 0 should match. Okay, now I still need to figure out what happens before I let go, after I catch it. When I throw the marker, the throw looks something like this. So when I catch it, what happens to the velocity? Okay, does it go to 0 slowly, quickly, or instantly? Now, so those are my 3 options: slowly, quickly, or instantly. Now what I mean by instantly is it took no time at all, really, literally. Quickly means it took a very small amount of time, and slowly means it took a longer amount of time. That was a little vague there. So can the marker come to a stop instantly? Okay. It's a good thought. See, some of you thinking, well, I don't know. Can it? What if it hits the ground? Does it come to a stop instantly?
It bounce.
So if it did come to a stop instantly, that means the acceleration, just change in velocity over change in time. Let's say this is negative 5 meters per second. If I came to a stop instantly, my acceleration would be change in velocity, negative 5, divided by 0 time. So my acceleration would be what? What's 5 divided by 0? Would be infinity. So I have an infinite acceleration. What force would be necessary to produce an infinite acceleration? Infinite force. So am I going to get an infinite force? And if so, if I did have an infinite force, the marker would be pulverized. Okay? So I'm not going to get an infinite acceleration. I might get a very large acceleration. It might stop very rapidly. And the more rapidly it stops, the greater the force is acting on it. So if I were to land this on a pillow, it'll stop a little more gradually. So the force of the pillow acting on the marker would be smaller than if I landed it on a rock. If I landed it on a rock, it's going to stop very quickly, so the force is going to be a lot larger. So the greater the acceleration, the greater the net force acting on the object. So actually, it's not going to stop quite that instantly. This is landing on my hand. So that slope right there will have some slope to it. I think, though, the acceleration will be steeper, though, or in other words, more acceleration than the negative 9.8. The acceleration of me catching it, the catch is pretty fast. How about when I throw it? When I throw it up, what do you think is more abrupt? The throwing up of, like the accelerating of it to get it moving, or the catching? Catching, more abrupt. So therefore the throwing of it, the accelerating as I throw it in the first place, on the up, I think would be a little more gradual. So I might write that a little more spread out. Some of you had kind of this shape. However, if you drew this as your velocity versus time graph, I would say that's wrong. You've got kind of the right idea that it's positive and then negative. Okay, so kudos for that. However, in this case, we have a fixed, steady acceleration. So a key feature of this graph is that we have this steady acceleration while it's in the air, and the slope of this line would be negative 9.8 meters per second squared. A common mistake would be for people to think the object is at the top here. What's actually happening at this point right here? What's happening to the marker?
It's changing direction.
At the top, you mean? Changing direction from moving up to moving down?
Yeah.
No, that's
Oh,
actually
sorry. I thought that was. Sorry.
So right
Yeah.
here is when I've released it. So this instant right here, the acceleration switches from a positive acceleration to the negative 9.8. That instant right there, where I switch from my hand pushing it up to the negative 9.8, is what's happening at that point right there. All right, now that we've got the correct velocity versus time graph, you should be able to graph either position versus time or acceleration versus time. I think the easier of the two is an acceleration versus time graph. So see if you can make an acceleration versus time graph corresponding to this motion. Only while it's in the air.
Yeah.
Only while I've let go is the acceleration negative 9.8. So I want your graph to start
Okay, start
here and go all the way
at
there,
the time.
not just for the time. Where it's
Gotcha. Yes.
Okay. Graph, while it's in the air, the acceleration is negative 9.8. Before I let go, it's accelerating upwards with a positive acceleration. The exact shape of that, I'd have to accept just about anything. Because to know the exact shape of that curve, you'd have to know exactly how my hand was pushing on that marker. So if you rounded this, if you made it a triangle, if you made it a square, all of those are equally valid answers because you don't know, all happened too fast to know exactly how rapidly I was accelerating that marker. However, if you rounded this part, or made that into a triangle, you'd be wrong. Because because there, for this situation of throwing the marker up and down, there isn't enough air drag for it to be significant, so we are accelerating at a steady negative 9.8. When I catch the marker, the acceleration is positive, so the velocity goes from a negative number to 0. That results in a positive acceleration, so when I catch it, the acceleration will look something like that. It's a large number, and I noticed a lot of you on your graphs showed the catch to be a bigger number than the original throw, and I like that. That's good. The total area under that curve. Total area under that curve would be the integral of A dt. The integral of A dt would be the total change in velocity. The total change in velocity, let's see, that's from when I start,
0.
stop. The total change in velocity between the start and the stop was how much?
0.
0. So the area under that curve better be 0. Is it plausibly 0? Well, I've got some positive area, and some negative area. So yes, I think it's plausible to add up to 0. If you had only positive area or only negative area, we'd know no way could the area under that curve add up to 0. Where is the marker at the top? Up there. Okay, at the top. Where on this graph is the marker at the top?
The middle, the bottom.
Yes. Right there. Where on this graph do I let go of the marker on this way up?
Top of the first positives. Both.
And I'd accept here, here, or anywhere in between. So Roger picked that top point. Sounds good. Okay. All right. Let's make a graph of position versus time, and then we'll move on to an acceleration as a function of x. And let's say that when I am first holding the marker at rest, that corresponds to position 0. So first, this right here is position 0. This is the positive direction. Anything lower than that would be a negative position. See if you can make a graph of position versus time that correspond to this situation.
You're improving it?
Good. That's much better. Okay, let me look at the situation like I did last time. The middle part first, and then we'll tack on the throw and the catch at the end. In the middle part, I have a constant acceleration. During the middle part, I have a velocity that starts off at its biggest, and then very steadily goes from positive 5, positive 4, positive 3, positive 2, positive 1, 0, negative 1, negative 2, etc. My velocity changes at a linear rate, changes very steadily. The velocity is the slope of the position versus time graph. So that means my slope has to change gradually. So the slope of this graph can't suddenly jump from positive 5 to negative 5 or something like that. It has to go gradually. The slope has to slowly go 5 to 0 to negative 5. So during the time where it's in the air, the slope starts off at 5, and then very gradually gets less and less steep, then very gradually gets more steep. Okay? So the shape has to be such that the slope is gradually changing. Many of you had like a peak, a triangle shape, and that would be incorrect because what you'd have there is the steady slope going up and then very abrupt switch from a positive to a negative. So while it's in the air, it's going to take on this shape here. As I'm throwing it up, what happens is the velocity starts at 0 and then increases up to 5. So my velocity, actually I need to move this down just a touch. My velocity starts off flat and then slope increases until I'm at a maximum slope of 5. And when I catch it, that's going to occur, but it's going to occur a little bit faster. So the catch, the slope is going to change very rapidly down to 0. So the graph should look like that. Where on this graph is the marker at the top? Okay, here on a position versus time graph, it actually is at the top. Where on this graph do I let go of the marker? Maybe it's hard for you to describe. Let's try it again, Eric.
I don't know, that bottom curve, bottom left curve.
Like here? What were you thinking?
Yeah, around there.
It's wherever the slope is steepest. So wherever it's going the fastest. It's going the fastest the instant I let go. So here the slope isn't very steep yet. The slope is flat, 0. Then it gets steeper, and then starts to curve back the other way. So this is where we let go. Okay. Again, this is a pretty, at least initially, a pretty innocent looking situation. All I've done is taken a marker, throw it up, catch it. We have not yet worked in air drag. We have not yet looked at more complicated